Well, I want to peel the layers back about how we forecast the weather, because you might just think, it's low pressure systems, it's cold fronts, it's warm fronts. It's actually a lot deeper than that. And by deeper, I also mean deeper into the atmosphere, because we're not just looking at what's going on here at the Earth's surface, but also what's above us. So when we start the forecast process, we usually start up at the top. It's a top-down approach to weather forecasting, and let me explain why. So here we are at jet stream level, about 30,000 feet in the atmosphere. And if you'll notice, that's also about airplane cruising altitude. If you notice when you fly and they say, hey, we're going to be cruising at 35,000 feet. Why do they cruise at that level? Well, the first level of the atmosphere closest to the Earth's surface is the troposphere. Then you have the stratosphere, which is above that. Well, the troposphere is where all the weather occurs. But once you get into the stratosphere, which is the next level of the Earth's atmosphere, the air starts warming. So you don't get cloud formation typically in the stratosphere, and the weather is a lot calmer. Skies are clear. So typically, airlines like to fly where the weather's quiet, right? Which is at the lower level of the stratosphere. Now that level can vary based on the weather, but again, it's roughly at 30,000 feet. So from a weather forecasting standpoint, this is where we start. And we are looking at the winds at this level. These are the jet stream winds. And the jet stream does a couple of things for us. Number one, it divides cold air to the north from warm air to the south. And number two, we really look at this as well for these dips or troughs of low pressure and ridges of high pressure. So if you'll notice on this map, there is a ridge of high pressure right over the upper Midwest. So this gives us a broad view of the general weather pattern. And again, here in the mid-latitudes, we have the westerlies. You may have heard of that before, where our winds are typically blowing from the west to the east. Now, of course, that's going to vary based on these troughs and these ridges. That, in turn, plays a role on how cold or how warm we get based upon that wind direction as well. All right, now I'm going to take you a little bit farther down to 18,000 feet. Now, why do we look at this particular map? Well, you might look at this and go, that's interesting temperature-wise, but actually these aren't temperatures. They're correlated, which I'll explain, but the colors that you're seeing here are called geopotential height, and these are the lines that you're seeing on here. What on earth does that mean? Well, as meteorologists, as we look at this, this is approximately 18,000 feet as to what we're looking at, but it's actually changing on here because this is really a pressure level of 500 millibars. All right, so typically on television, we talk about air pressure in inches, right? Inches of mercury. But in meteorology, we look at it as units of millibars. And so this is 500 millibars, which is approximately 18,000 feet, but temperature changes that. So, well, these heights are technically not temperatures. How it can be correlated is the higher these heights, the warmer the temperature. So what this means is where you're seeing these lines, these height lines, if you will, is the height in the atmosphere where you hit 500 millibars. So if you were to take a hot air balloon and go up and you hit 500 millibars, it would be at these particular height levels. And this is important because this goes back to what we talked about a minute ago with troughs of low pressure and ridges of high pressure. So we look at a map like this to continue to denote where these areas of low pressure are, and we actually dive even further into maps like this as well. Now I'm going to take you even lower. Remember this top-down approach, right? So now we're at approximately 5,000 feet, or otherwise known as 850 millibars. This is showing temperatures, and you'll notice it looks somewhat close to that map that I showed just a moment ago of that geopotential height. And I'm showing you this because you'll see that trough of low pressure with time, eventually you start to get that cold air coming in to the upper Midwest. And something else I'll point out about this, I will typically show this on the air, and we'll show this on the air to show temperature trends. And you might be thinking, wait a minute, why would you show temperature trends at 850 millibars, which is about 5,000 feet above our heads. Why would you show that for temperature trends and not at the surface? And the answer to that is because this map, because it's a little bit elevated in nature, is showing us the general air masses. It is not taking into account what we would call the diurnal temperature variations at the surface, meaning it gets colder in the morning, right, and warmer in the afternoon when the sun comes out. We don't see that on this map. So this is a better way to diagnose and prognosticate temperatures going forward because it doesn't have that morning cooling and afternoon warming, so we can go and look through the future like this to see the general temperature trends without that daily variation getting in the way. All right, now I'm going to take you down to the surface. So again, we started out way up there, right, at 30,000 feet. And now here we are at the surface. Now in this case, you can see a frontal boundary, a warm front that is set up here. But before I dive into this, I once had an email from a viewer, and it was very interesting because the viewer said, look, you don't always show fronts on your weather maps. And he was pretty upset about it, to be honest. I'm really upset that you're not showing frontal boundaries on your weather maps. And my response was twofold. Number one, sometimes fronts are not significant to the weather story. It might be a little bit of a wind change, but it's not overly significant, so it can lead to bad messaging, if you will. A cold front doesn't always mean a sharp drop in temperature, right? But number two, you can have storm systems and you can have rain without frontal boundaries. Why is that? That's because when we go back upstairs to 18,000 feet or to 30,000 feet, you can get these perturbations in the atmosphere. Think of it like a river, right? We talk about the jet stream being a river of air in the atmosphere. If there's a little rock, a little pebble that's thrown in there and you get that ripple effect, you get these little storms. They may be too small to form any fronts, but yet we still get rain from it because it's not just what's happening at the surface, it's what's happening above us as well. So that's why fronts, that's really almost the last thing that we look at because it's not always significant to the weather forecast. What's going on above us really is typically much more significant. Now, in this case, we do have a surface frontal boundary. So it starts, it forms way above us, and it builds down, right? And then you get this area of low pressure that develops. Now, these areas of low pressure develop from temperature differences way above us at the jet stream level. Those temperature differences lead to pressure differences, which leads to this area of low pressure forming. The Rocky Mountains in our country plays a big role in areas of low pressure developing. Why is that? And I'll get deeper into this likely in another episode, but as storm systems move east of the Rocky Mountains, well, they get crunched when they move over the mountains. When they come down, they spin faster, form these areas of low pressure. So the mountains play a big role for us. So then you have this warm front, which in this case turns into a stationary front. So that's why it looks a little different the farther south you go. That just means it's not moving for a time. It'll go back into that general warm front formation as it continues to move. And then you have a cold front farther off to the west. Now, warm fronts and cold fronts obviously do different things. Warm fronts will typically warm us up. It can also bring rain before it comes through. That's, again, another topic for another time. And then the cold front, that if it has a fair amount of cold air or less humid air in behind it, that would be what we call a dry line out on the plains. That causes the air to converge, causes the air to rise, and that's why you get showers and thunderstorms or snow along a cold front. So again, so many factors when it comes to weather forecasting, but the big takeaway here is it is a top-down approach. And I know folks might think, oh, weather forecasting, oh, it's easy. Nope, this is why I have gray hair. There are so many factors when it comes to meteorology, and we're literally just scratching the surface a little bit. But again, often it's not about really what's happening here at the surface. It starts way above us.